So is this function is clear?
Yes.
Okay. Or any doubt in BIC?
Sir, આમાં destination register R2
Destination register?
એટલે R2
What is
કે
No, destination register is R0.
ઓકે સર સમજાઈ ગયું.
So ultimately, it's something like this. BIC, I will write it here so that it becomes very clear to you. This register is RD and RS1 and RS2. So these two registers will perform the operations and the result will be stored in RD. So the full form of BIC is a bit inward clear. So it will basically. Any question?
No sir, no question.
So it's very much useful in manipulating status flag and it is acting as an interrupt mask. So if you want to mask some interrupt, then corresponding bits, whatever the bits are 111, corresponding bits will become 000. So it's basically a masking process. So it will mask your interrupt. So this bitwise, this is very useful bitwise logical operation. Then OR operation. OR operation is normally the syntax is like this: ORR, RD, RN, and operand. So it performs basically bitwise OR operation between the register RN and value of operand 1. So this operand can be any register or any immediate value, and the result will be stored in the destination register. So if you look at the examples of this instruction, ORR, R1, R1, R2. So it will perform OR operation between the R1 and R2, and the result will be stored in R1 register. ORR, R1, R2, you can also specify some immediate value. Right? So operand 1 can be immediate value or it can be some register also. It basically performs the OR operation. Then similarly AND operation, it will perform the bitwise AND operation. Syntax is again very much similar to OR operation. Like it has a RD, it's a destination register, the register and then operand. So this operand can be any register or it can be any immediate value, right? So that you can specify there. So it will perform logical AND operation between the R1 and R2 and result will be saved in R4. It will perform logical AND operation between R2 and 55 and the result will be saved in R1. Now suppose I have a content in R1 initially 0x FF. And the content in R2 is, let's say, whatever you have transferred here is will become how much if if you basically consider that initially you have a 0x55, let's say. Then what will be the content of register R4 after executing this instruction and instruction? Can anyone tell me?
repeat કરજો ને એકવાર પાછું.
The value of R1 is 0xFF. Value of R2 is 0x55. And we issue this instruction. So after execution of this instruction and R4, R1, R2, what will be the value of R4?
Sir, 0x5.
0x55. Very good. So because FF is 1, 1, 1, 1, all ones, and this 55 means 0, 1, 0, 1, 0, 1, 0, 1. And we perform the AND operation, the input of AND gate is both are 1, then output will be 1. If any of the input is 0, output will be 0. So your output will be 0, 1, 0, 1, 0, 1, 0, 1. So it remains 5, 5. Okay. Now this is your value available in R5. And now let's say that in this case, let's say your initial value of R2 is 0x AA. And then after you perform this operation and R1, R2, hash 55, what will be the value of R1 after executing of this second instruction?
Sir, 0, 0.
It will be 0, 0, right? Perfect. Okay, fine, good. Then there are compare instructions are there in ARM. CMP, R0, R5. Okay, anybody, can you tell me what is the instruction for logical NOT operation? We have seen the AND operation, OR operation. What is the instruction for logical NOT operation? We have already seen in our first lecture, say MVN, right? MVN, R2, R1. So the logical NOT will be performed on R1 and then it will be transferred to R2. So it is a kind of a data transfer as well as it is also we call it as a logical instruction. So data transfer along with the logical NOT operations is done in this instruction. So in a compare instruction, what it will do, it will compare two registers and based on the comparison, flags will set. So let's consider this instruction compare R1 with 0 and be any loop. So if it is not equal to so if 0 flag is not set, then it will branch to the loop. So after this compare instructions, you can use the conditional branching instructions. So in this case, the first instruction will compare R1 with 0. The second instruction is a branch instruction. The program will jump to a location specified by the label loop if R1 is not equal to 0. If R1 is equal to 0, then branch will not be taken. If R1 is not equal to 0, then branch will be taken. Then one more instruction is a TEQ. So it will perform the exclusive OR operation between the R1 and R2. And based on the result, the flags will set or reset. So TEQ is for exclusive OR operation. Then TST, R2 and R3. So what it will do, TST will perform the AND operation between R2 and R3. So basically it is R2 and R3. And based on the result, the flags will be affected. So it is a TST. Any doubt in these instructions? Okay, there are no doubt. I will go ahead. Comparison instruction in that you can also add N. So when you add the N here, it will compare R1 with a negative of R2. Similarly, CMN R1, 0x55. So it will compare R1 with negative of immediate value 55. So that type of comparison is also possible. So it is comparison along with the NOT gate. Logical instructions we have already seen, exclusive OR operation, that is EOR. AND operation is that is AND, and OR operation is ORR. So these are the logical instructions for a typically AND or exclusive or gate. And you can always use immediate value here instead of R3. If you want to use some immediate value, you can use it, okay, for all these three instructions. Then modifying the status registers. So we have a status register CPSR that you can modify indirectly. So there is a one MSR which moves the content from CPSR or SPSR to selected GPR. So MSR, if you use that, it will transfer the content of CPSR to register, specified register. Okay. This is how you can modify the status register. Then once it is available inside the registers, you can modify the content of register, and then after you do the MRS, moves the content from selected GPR to CPSR or SPSR. That means you cannot directly modify the CPSR, but first you have to transfer CPSR to registers. You modify the value of register and then copy it again to the CPSR. So we have to use MSR and MRS operations. MSR means it will move the content from CPSR to GPR, and MRS means it will move from GPR, that is from register, to status register, that is CPSR. And of course, this can be done only in a privileged mode, right? So you have to use some software interrupts like SWI to go to privileged mode, and then only you can do this operation. In a normal mode, in a user mode, these operations are not permitted. Then there are shift operations. We have already seen few examples of the shift operation, that is a LSL, logical shift left. And this instruction you can use with other instructions like move, add, and many other instructions, right? We have also used this with load and store operations. So in a logical shift left, the MSB will be transferred to the carry flag, and LSB 0 will be inserted in that. Okay. So, and essentially this is instructions will multiply with the power of 2. So every time, you know, the content of registers will be multiplied by 2 with help of this instruction. So these are the examples. Move R0, R1, LSL2. So it will logically shift left the content of R1 by 2-bit position. So essentially it will multiply R1 by 4 and it will transfer to R0. So essentially after execution of this instruction, R0 is equal to 4R1. And this instruction means it will logically shift left content of R1 by a bit position specified in R2. And then it is transferred to R0. So logical shifting you can add along with the instructions. So that is the beauty of ARM architecture. Logical shift right is exactly, you know, in this case, all the bits are shifted to the right side. Okay. That means it will divide the number by power of 2. So if you are shifting by 1-bit position, it will divide by 2. If you shift it by 2-bit position, it will divide by 4, like that. But here LSB will transfer to carry flag, and MSB in that zeros will be inserted. Okay. So again, you can combine this with this data transfer instruction. So in this case, R0 is equal to R1 divided by 4 because we are shifting left, shifting right this R1 by 2-bit position. So essentially it is very much similar to by dividing by 4. And in this case, we are shifting right number of bit positions specified in register R2. So then you can use all these instructions along with add also. You can use these instructions along with the move, along with subtraction operations, And in data transfer also, we have used this to specify the offset value. Then there is a barrel shifter that is actually arithmetic shift right. So how it is different from the LSR? Because arithmetic shifting right, in which we are trying to preserve the carry flag. Carry flag should not change here. Not carry flag, but sorry, a sign flag. So because this is a sign bit, most significant bit is a sign bit. So that sign bit should not change, right? So suppose if you have a, let's say, value like this, 1111, 1111, this means it is a negative number, -1, right? And if you use simply LSR, what will happen? 0 will be inserted here, and this 111 will shift in this way. What will happen? This number will become 7, right? So this negative number is changed to positive number. So that is the error introduced due to the LSR. So in ASR, if we do, in ASR, the sign bit will be preserved. So sign bit will be kept as it is. The remaining bit positions will change. Okay. So all these remaining bit positions will change. So every time, whenever you perform the ASR, the sign bit will be preserved. It will be copied there itself. So it will not change. So that is the beauty of this ASR. Then another one is ROR, rotate right. In a rotate right, actually, the LSB will transfer to MSB, as well as LSB will transfer to carry flag. So it bit rotate with a warp around from LSB to MSB. So in this case, if this is a 0, then 0 will transfer to MSB. So maybe that's your sign flag will not be preserved. So in this case, LSB, that is less significant bit, will move to carry as well as to the most significant bit position. And one more is RRX. RRX is a rotate right in extended position. So in that case, the LSB will transfer to carry flag will transfer to MSB position. So LSB will not directly transfer to MSB, but LSB will first transfer to carry flag, and then carry flag will be transferred to the MSB, most significant bit position. So that is how RRX will work. So these are the different versions of rotate instructions. Okay, any doubt in this instruction? ASR, ROR, RRX. Okay, if you do not have any doubt, let's discuss few more instructions. So this is how barrel shifter will work. We are specifying the operand 1 and then operand 2, which is given to the barrel shifter, and then it is given to the ALU, arithmetic and logical operations. So in our example, if we write move R1, R2, LSL has 2, then R1 is your operand 1 and R2 is your operand 2, which is essentially logically shifted left by 2-bit position, and then it is given to the ALU. ALU will perform the job and then it will transfer the content to the R1. So your result will be there in the R1 register. Then there are many multiplier instructions are also there in ARM. Multiply and accumulate instructions are also there. So there is the integer multiplication, which provides the 32-bit result. Long integer multiplication, which provides 64-bit result. Then there is a built-in accumulate unit. So that is called MAC unit, multiply and add unit. So multiply, accumulate instructions and add product to the running total. So that type of instructions are also there. Let's look at all these instructions. There is a MUL, that's called multiply, simple multiplication, 32-bit result will be there. Then MULA, multiply and accumulate, again the result will be 32-bit. Then UMUL, that means unsigned multiply, 64-bit result. Unsigned multiply and accumulate, 64-bit result. Sign multiplication, that is 64-bit result. And sign multiplication, that is again 64-bit result. So all these are the different versions of multiply instructions. So if you perform the unsigned multiplication, the sign will not taken care. And if you perform the signed operations, signed multiplication, then sign will be taken care. That means if you, let's say, multiply -1 into -1, the result should be 1, right? But that -1 in a binary, it is represented. If you look at 8-bit positions, then FF it is represented. FF multiplied by FF. Right? So that will become 1 if you are performing a sign multiplication, right? If you perform unsigned multiplication, what will happen? 255 into 255, right? So it will be a 65535. So there is a huge difference between the signed multiplication and unsigned multiplication. In an unsigned multiplication, MSB is not considered as a sign bit, and all the numbers are considered as a positive numbers, right? So this FF hexadecimal value, if you consider this as a signed number, then it is a -1. But if you are considering this as an unsigned number, then it is a 255. So there is a huge difference between the signed number and unsigned number. Okay. Compare and test instructions already we have seen TST and TEQ. So TST is basically performing the AND operation, and the flex will be affected. TEQ will perform the exclusive OR operations. Compare will compare the two registers or one register with some immediate value, and it will update the CPSR based on the result available in destination register. TST and TEQ, which we have already seen. So AND operation and exclusive OR operations. So now let me show you these programs. I will run these instructions in a kill, and then we'll come back to this PowerPoint slide again. So some instructions are written here in a kill program. So these are the assembly language instructions which is written here. We'll build this program first. Is the screen visible to all of you, or any doubt?
Yes, sir. Visible screen.
It's visible. So I will debug this first. So when I will debug this, first instruction is simply transferring 1 to R1. Second instruction is simply transferring 5 to R2. Then R1 and R2 logical OR we are performing. So it will essentially remain 5. Will not be any change. Then R2 and AA we are performing again OR operation. So it is becoming FF. Then we are performing logical AND between R1 and R2. So R1 is 55, R2 is also 55. So naturally result will remain 55. Then R4 and 55. So result in R4 is 55. So again it will remain 55. Then TEQ, that is, it will perform the exclusive OR operation between R4 and 0x11. R4 is 0x55 and R immediate value is 0x11. So it will perform the logic exclusive OR operation, and the corresponding CPSR will change. So CPSR value, as you can see, the 0 flag is 0. Then I and F is 1. So no flag is set here because the result is not 0. So that's why. So you can modify the values here and perform the write different instructions, and you can check all these instructions how it works. Later on, I will give you laboratory exercise, and you have to solve that laboratory exercise, and then you have to give it results to me. Right? Let me see how many. સુકેશો મિત્ર તારો અવાજ બરાબર નથી સંભળાતો.
આપણે આમાં ઇનડાયરેક્ટ એડ્રેસિંગ કરીએ તો કઈ રીતના ફેર પડે કઈ?
એ એડ્રેસ ઉપરથી ડેટા લઈને ઓપરેશન કરે.
ઓકે.
So out of 90, 62 turned in. So laboratory quiz, 62 students have completed the laboratory quiz. Others are still remaining. So whenever I put any learning quiz or laboratory quiz, immediately try to attempt the quiz. Okay. So later on, I will put the learning quiz based on these logical operations. In which, suppose if you read it is a complex calculations, then you can use skill IDE to complete the calculations. Okay. Then there are branching instructions. So it's very simple in ARM. In a branching instruction, simply B is written, right? Branch, B for branch. And then you have to specify some condition. So I can write a simple instruction like this. You can write instructions in this way. B here. So it's a simple branching instruction. It's very much similar to your while one loop. Simple branch instruction is there. It's not space here. We'll write it here. While loop. So notation is B and then some address. So it can jump forward or backward direction up to 32 MB space. Okay. Then there are conditional branchings are also available. So in that, after B, you have to specify the condition. So for example, B and E, branch if not equal, right? B and E. You can also write BEQ, branch if equal, right? And then the loop, name of the loop, let's say BEQ again, or whatever the label you want to give, you can give it. So it is a conditional branching. And suppose this BNE loop is given after this execution, CMP R1, 0, then program will jump to the location specified by the loop label if R1 is not equal to 0. Right? And if you use this instruction, then program will jump if R1 is equal to 0. Right? So you can specify the condition after branch, as well as you can also take unconditional branching. Then there is another one, a branch link BL. It is same as B, plus it saves the next instruction, is PC plus 4 into the link register. So now it's obvious that whenever you want to return back to the main program, you should use BL instead of simple B. Because in simple B, whenever you transfer your program to some other location, it is difficult to come back because original location we don't remember, right? So if you want to take a jump to some subroutine, then you can use BL, right? So BL, we can say it is very much similar to the call instruction, okay? Because in call instruction also the program counter is saved into the link register. Okay. So branch and link is very much similar to B, but additionally it will save the next instruction, which will be executed if branch was not occurred. Then the next instruction of main program will be stored in the link register. So if you want to come back, you can use that link register. You can copy that link register again to the PC to come back to the main program. Is it clear or any doubt in this?
No, sir, no doubt.
Okay. So BL is suitable for function call and return value. When subroutine is finished, it can return to the main program by copying the content from link register R14. So you can use instructions like this: move PC LR. So link register will be transferred to PC and your program will be returned to the main program. Then there is one more branch instruction, that is a branch and exchange, that is a BX. This instruction is executed only if the condition is true, and instruction performs the branch copying the content of general register Rn into the program counter. So the value of register will be copied to the program counter. So naturally the branch will be taken automatically, right? So PC value will be stored in the register and register value will be transferred to the PC value. So it is called branch and exchange. So branch exchange, branch link exchange is very much same as B and BL, that is unconditional branch and unconditional branch with a link register. Exchange instruction set and is available ARM and thumb mode. Okay. To return from subroutine to the main program, the return instruction is not there in ARM processor. In AVR, we have studied the return instruction, but in ARM, there is no return instruction. So we have to use this instruction, move PC, R14. Okay. So R14 is your link register. It will be transferred to the PC and you will be able to return to the main program. So there is no RET instruction in ARM processor. As we have already seen, two type of branch instruction. B is ordinary branch instruction. BL is a branch and link instruction. So BL performs the branch operation and save the address of following branch, that is return address, into the link register R14. So you can specify it like BL and then name of the subroutine where you want to take a jump. Now this is very important. That is a conditional execution. So all the instructions which we have studied, you can add condition code along with the instructions. So condition code specifies that which bits in CPSR need to be tested. Condition codes used in branch instruction B is given in following table. So you can add all this condition code along with the branch instruction, like along with B, you can add EQ, so it becomes BEQ. Along with B, you can add NE, so it becomes BNE. Along with B, you can add CS, BCC. So all these condition codes you can add. Like MI, if you add, it will become BMI, then BPL, BVS, BVC, and so on. Not only with the branch instruction, this condition code you can also add with the move instruction, like move EQ, move CS, and so on. So in next lecture, we will give more focus to these condition codes, conditional execution. It's very important in ARM processor. And when you use these condition codes, it will prevent the frequent branching. And because it will prevent the frequent branching, you don't require to flush pipeline again and again. Because you know that in ARM, we are using a pipelining architecture. So whatever instructions you are currently executing, next instructions are already there in a pipeline. But after execution, you came to know that, this is a branch instruction. So now you don't want to run the instructions which are already there in a pipeline. Then you have to flush the pipeline. So if you use more branch operations, branch instructions in your program, you require a frequent pipeline flushing. And because of that, the throughput will reduce. So to prevent that, in ARM, there are condition codes are given. So if you use these condition codes wisely along with your assembly language instructions, then you will be able to reduce number of branch operations, and you will be able to reduce number of pipeline flush, and you will be able to increase the throughput of your program. So I think I will stop here. If you have any doubt, any questions, you can ask. Otherwise, we will end the meeting. So let me take first of all your attendance. Any doubt, any questions?
No, sir, no doubt.
No doubt. So are you enjoying this sessions or any problems? Because AVR, all of you have done the programming. Similar programming you have to start for this ARM. And in ARM, there are many boards are available. So how many of you have purchased the Node MCU boards or any other ARM board? Because you have to do some laboratory experiment at home. So okay, I am seeing that some hands are already raised. That's good. So it's better that you do the experiments at home. And Niranjan sir is guiding you about the laboratory experiments. Do some innovative experiments. And you can also use C language, and you can use assembly language. You can use Arduino language. Later on, I will show you the Energia software. Energia is very much similar to Arduino, which you can use for the ARM processor. Okay. Thank you all for attending the meeting. Goodbye.